Hello everyone, my name is Shixun Huang and I'm from MIT University. The title of our paper is Influence Maximization in Real-World Closed Social Networks. This is the joint work between MIT University and Tensor. Many existing social networks are open, meaning that the posted message is available to all online users. However, closed social networks are becoming more and more popular. So in those networks, the messages is only shared with limited friends. So this sharing model is favored by Generation Z, who emphasize the privacy. So the main difference between closed and open social networks mainly relies on the sharing model instead of the network topology. Our research goal is to recommend K existing friends to spread and maximize the seed's influence. And we consider the independent cascade model as the diffusion model. And actually, each friend's recommendation refers to one directed edge, since we are recommending K friends for multiple users. So those edges actually can form a diffusion subnetworks, which is called K subnetworks. So in the K subnetworks, each node can only has at most K outliers. So we aim to find the optimal K subnetworks to maximize the influence of the CSAT. In the example below, when we set K equals to 2, then the diffusion networks formed by red edges only is actually the optimal K subnetwork. Here's our contribution. We take the first attempt to address the influence maximization in closed social networks as a research problem and prove it to be NP-hard. And our method notably outperforms baseline on the variance of this problem, including deployment at real-world applications. Here is the solution overview. We first focus on solving the case with a single seed, and then we work on extending the solution to solve the case with multiple seeds. Here's the sketch. Our iteration is to insert edges from the original network into the initially empty subnetworks. And the strategy is to greedily insert edges with the maximum marginal gain. However, we find that the marginal gain is not self-modular. So to improve the theoretical performance, we resort to use a new model called RMPP model, which estimates the lower bound of the influence and preserve the submodularity. So in this model, it defines a path called a restricted maximum probability path, which has the highest influence probability among all paths containing at most one inserted edge. So the influence will be the influence probability of all paths from the source node to all other nodes. In this example below, we have two native edge, SB and BC, and three candidate edges for insertion. If we insert all of them, actually the influence of S over E is still zero because we have to traverse more than one inserted edge to reach E, which is not allowed in this model. And if we only insert edge SC, the influence of S will be 1.5. Similarly, if we insert edges SC and CD, the influence of S will become 1.75. So even we use these new models, we still cannot reach those further away. So to remedy this situation, we're trying to reinsert edges iteratively, and at the end of each edge, we mark inserted edge as native one. For instance, now we have three candidate edges, and K equals to 2, then we choose 2 out of 3. And then at the end of this iteration, we mark those inserted edge as native one. And further to choose candidate edge for new users included in this subnetworks. And we keep doing this until no edges can be inserted. So our solutions have four components. The first one is the augmentation sketch, which is algorithm one, and it includes the edge insertion sketch, which is the second component. And then we will focus on optimizing these two sketches by proposing practical augmentation, and edge insertion. So for the edge insertion sketch, we try to greatly insert edges until no influence increment. However, this naive way is costly because there are too many edges for comparison. So actually observe that among all candidate edges sharing the same end node, there exists a critical edge, which means that inserting all other edges after this critical edge will not increase the influence. So we just need to consider the critical edges in the greedy strategy, which greatly prunes the space. So to define the critical edge, we need to define the strict maximum probability path first. So it has the highest probability among all paths containing native edge only. So it's a special case of RMPP path. So for instance, here, the critical edge is actually CE because after we start in CE, inserting BE and DE will be not meaningful because the RMPP path will always be SCE. So for the practical edge insertion, even we identify the critical edge, but it's still very costly because there are too many marginal gain comparisons. So we are trying to predefine our insertion order. For instance, suppose we have an expected order A, B, C, D, which is computed by the previous costly greedy strategy. We aim to use a simple process to proceed or guess a cheap order, such that following this order to insert the edges and the actual edges being inserted are similar to the expected edge insertions. So we can achieve similar outcome. So to do this, we need to compute the order. We are based on prioritizing those which appear in many SMPP paths to different nodes. Okay, to quantify the appearance, we just need to construct a SMPP based graph, which consists of all SMPP paths. And we just need to compute the size of the subtree usually at each node. And we sort those nodes based on their subtree size. So we think that a node which appear into many SMPP paths will have great influence. So this order should be pretty similar in theory to the one we computed with the costly greedy strategy. And the time complexity can be greatly reduced. And about the augmentation, we find out that the previous one is very expensive because the graph we need to construct the candidate graph in each iterations. And we also insert very limited edges in each iterations. So to improve the efficiency, we have several observations. The first one is that actually the candidate path at the current iteration just introduced some new edges upon the previous candidate path. So we just need some incremental update. And we find that the influence spread and node size in the subnetworks will converge after few iterations, which means that the subtree size based ordering will also converge. And the candidate path at the current iteration literally, at the last iteration literally becomes the one at the current iteration. And we propose a fast greedy simulation techniques, which is able to simulate the rest of the iteration after convergence in linear time. And now we talk about the solution for multiple seeds. So the trivial extension is not feasible because we have CD-dependent critical edge. And it's very hard to predefine the pre-process order. So we observe that actually an edge insertion have different impacts on seeds. So we resort to identifying the relevant seed, the seed that might be impact most by inserting edges to a node U. And then for node U, we identify the critical labor based on the relevant seeds of labors. So we can actually each seed and the nodes with this seed as the relevant seed forms a SMPP base tree. So actually, we can do this for all different seeds, and we can form a multiple disjoint SMPP base tree. And we can order nodes based on the subtree size. The naive way to identify a label is to compare SMPP paths from every seed to each node, which is infeasible in practice. Okay, then we introduce a more efficient approach. We introduce a virtual node X and connect X to every seed. A, B, C are the three seeds in our example with the influence probability 1. Then we can actually simplify the case to with multiple seeds to the case with one single seed X based on the equation below. So this is the definition of critical neighbors for multiple seeds. So actually this is equivalent to the definition of critical neighbors in the case with X as the single seed. We just need to do some minor adjustment by introducing node X and the edges connecting X and every seed. After we produce the solution, we just need to remove X and introduce edge. In the experiments, we consider two parts. The first one is influence maximization, and second one is user click-through rate maximization. For the first one, we consider various edge settings, including constant setting, uniform sampling settings, and a data-driven way, which is based on the friendship intimacy. We consider those baseline, degree-based one, friend of friend, and random-based, and their boosted version, which build upon the subnetworks produced by our method before the convergence. The results shows that the boosted version are much more effective than the original one. And our method before the convergence only contributes a small percentage of the total edges, which demonstrate the superiority of our methods. And our method is also very efficient and very competitive with those baselines. We also conduct experiments by varying the seed size, and the result shows that our method consistently outperform all boosted version. And our method is able to produce the solution on ORCUT within 2 hours, which is feasible in practice. And we also conduct experiment for different ratios. So here I ratio, E ratio, and N ratio refers to the seeds influence, the edge size, and the node size of the diffusion networks, as opposed to the counterparts in the input networks. And the result shows that our method is able to identify important edges and the nodes for spreading the influence. The last part is about click-through rate maximization. We consider an online battle arena game of Tencent. In this activity, user join the activity by interacting with friends recommended by the system, and the interaction stimulate the message receiver to further interact with others, and every user could be a potential and spontaneous seed. We use online A/B testing, and we use the top 10% of assigned user with highest degree as the seeds. And the results shows that our method is able to outperform all the methods, all of the rest of baseline. That's all. Thank you.